Hi everyone, we're going to finish up our work on our first set of notes on polynomials. So most of you should have these notes. It started with this classifying, adding, and multiplying. We talked a little bit about degree, about classifying polynomials, and I'm talking about their graphs. Now, on the second page of these notes, we did some adding and subtracting and multiplying. And the big idea when we were multiplying is that when we multiply polynomials, things can get messy, right? We really emphasize this idea of organizing our work. So there's this special type of multiplication that lends itself to kind of a shortcut, a way that's a little bit easier. Problems like this, where we have a quantity, a binomial, right? We have 1, 2 terms raised to a power. Now, what is x plus 2 to the fourth saying? Well, it's really saying, and let me slide over here, that we need to multiply x plus 2 times itself 1, 2, 3, 4 times. Now, if we do this the long way, the old-fashioned way, distributing, FOIL, right? We're going to end up foiling here, and then we have to distribute again. And then we distribute again, and you can see how long this whole process is. There's so many places where we can get, make arithmetic mistakes, drop an X. I'll be honest with you, I had to erase a few times because I made some mistakes as I worked through this. So this idea of multiplication with Pascal's triangle is just a way to help clean things up a little bit. So when do we use this? We follow when we have a binomial raised to an exponent. This template here is used in this table. Our answer will be a polynomial where the number of terms is one more than the exponent. I'm going to write that down, right? Terms is n plus 1, where n is our exponent. Our first term will be our a value, which I'll talk about more in a second here, to the n, and the last term will be b to the n. And then we follow a couple different patterns to help us simplify. So let me talk through an example here to identify those patterns. What you'll notice from the template is that there's an a value, a b value, and an n value. Our a value is the first of the 2 terms of the binomial, and our b value is the second term of the binomial. Here it is 3. Our n value is the exponent. So what that exponent tells me is that we will always have n plus 1 terms. In this case, we're going to have 5. And what this binomial expansion shortcut allows us to do is to get closer to an answer much quicker. So what I'm going to do here is I'm going to kind of map out 5 terms that we're going to fill in. All right, I have 5 terms. Why do I have 5 terms? Well, because the exponent was 4. That leads me to a polynomial with 1 more term than that. So I'm going to start with my a value, and I'm going to set my first term as a to the n power. In this case, x to the 4th. And then going left to right, I'm going to remove 1 exponent from my first term every time. And on the last term, I don't have any a value. I do the same thing with my b value, except going left. Instead of going from left to right, I'm going to go from right to left. So over here, I'm going to start with 3 to the 4th power, 3 to the 3rd, 3 to the 2nd, and 3 to the 1st. And then here's the one last part. We have to deal with Pascal's triangle. Pascal's triangle, you just watched a video about this, but it's this construction that'll help us identify some key coefficients for this problem. Now, we have 5 terms here, so I'm going to find the row in Pascal's triangle with 5 terms. I can see that it is 1, 4, 6, 4, 1. So those 5 binomials get plugged in front of each term. And then we simply multiply each term together to get our final answer. 1 times x to the 4th is just simply x to the 4th. 4 times 3 is 12 times x to the 3rd. 6 times 3 times 3, right, 3 squared is 9, gets us to 54x squared. 3 cubed is 27. 27 times 4 is 108. And finally, 1 times 3 to the 4th power leaves us with 81. So while that's not super straightforward and obvious, and it may take some practice, this process will repeat itself whenever we have a binomial raised to a power. Let's look at one more. Here we have 2x minus 1 raised to the 3rd power. I'm going to move this over just so we have a little bit more space to work. So in this case, my a value, and let's color code it this time, will be 2 times x. My b value will be -1. And my n value here is 3, which means the number of terms will be 1 more. That means I'm going to have 4 slots to fill. So I'm going to start with my a value. Notice that I'm going to put, I wanted to color code those, my apologies. I'm going to put my a value in parentheses. And then my exponent is going to go from n to n minus 1 to n minus 2. In this case, 3, 2, and 1. Going the other way, I'm going to take my b value, again in parentheses here, just to make sure we multiply appropriately. And I'm going to separate each of those with plus signs. All that's missing now is our coefficients from Pascal's triangle. So I go back up to my chart. I'm looking for the row in Pascal's triangle with 4 terms. I can see that 1, 3, 3, 1 are going to be the coefficients I need to multiply by. And now to finish this problem, I need to simplify each term. 2x to the 3rd power is 8x cubed, because that's 2x times 2x times 2x. Our next term, 2x squared, is 2x quantity to the 2nd power, ends up with 4x squared times 3 times -1, gets us minus 12x squared. Our next term, we are left with 3 times 1 times 2, so we have plus 6x, and finally minus 1. A couple things to point out before we wrap up here. When I have a quantity with a coefficient like 2x or 3x or something like that, the number and the exponent must be raised to the power. Additionally, when I have a negative value for b, my signs will alternate, right? Because when I raise a negative number to an odd power, I get a negative number. And when I raise a negative number to an even power, I get a positive number. So this is binomial expansion. You're going to move on to the multiplication worksheet and get some practice here before you leave. Thanks, guys.